TACoS Virtual Edition number 2. I'm Mrs. Kilty, and I'm going to be your teacher for the chemistry and geology sessions of TACoS. In this section of TACoS, we're going to do some cool activities that relate to chemistry and geology. Our theme for chemistry and geology is metamorphic rocks. So we're going to do a couple activities with those. We're going to look at how rocks become metamorphic and apply this to slime and looking at slime. And then our second activity is we're going to look at some actual metamorphic rocks that have been shaped into beads, and we're going to make a necklace. So let's go ahead and get started. First, we'll be looking at slime. Hi, now we're going to talk about the slime. Now, you should have gotten in your kit a bag that looks like this. It's got inside the bag a container, and in that container is your slime. It's about 2 ounces, more or less, of slime. There also should be a popsicle stick that you can use to stir it, and then an extra cup. And that extra cup is going to come in handy if you want to divide up your slime and do some different experiments with some of it, but not all of it. So that's a quick explanation of everything that comes in your slime kit. When you're done with your slime for the night, you can put the top back on. The bag is just an extra layer of protection for mailing it, and also if you really want to, you can put it into the bag at night. Now you might be wondering, how is it that we make this slime? Well, we made a bunch of slime by ordering it from a company and then mixing it up. This went into it, and it's colored green already, and this. So polyvinyl alcohol plus borax. And we put in the proportions, according to the recipe, is quite a bit more polyvinyl alcohol to less borax. And you can tell that even by the relative sizes of the containers we got, you use a lot more of the alcohol than you do the borax. What we decided would be the best thing is to do 40 milliliters of polyvinyl alcohol, and we mixed it right in the very cup that you got it in. And then they give you this, the borax, and we decided 10 milliliters. And the only reason why we didn't fill it to the fill line that they recommend is that tended to fill up the container all the way. And we thought maybe that was just a bit too much slime. But if you're interested, you can order this on your own. Okay, now here is the point at which we make slime. You can use your popsicle stick, start it stirring, and then add the slime very gradually. The borax to make the slime. Very gradually. Okay. It starts to get really thick, and it starts to kind of have the consistency of soft Jell-O. Okay, then it starts to go through a sticky phase where if you can see, it's like kind of sticking to the sides of the bowl. At this point, it's sometimes a good idea to take it off the popsicle stick and start kneading it in your hands to finish it off. Gooey, sticky. And then when it's about at this consistency, that's when we decided it was good to be packaged up and sent off to you. So this is about what your slime will look like when you get it done. All right. Now what we're going to do is look at the metamorphic rocks and the process of metamorphosis. That is our theme for the chemistry and geology section, and it kind of goes with the slime. So if you have gotten your slime out of the container, you can go ahead and keep kind of mushing it around in your hands as you watch this um, brief bunch of slides and the next bunch of slides as well. You don't have to put it away. You can sort of roll it around in your hands and fool with it as we're going through this material if you like. So we're going to start with this. This is what? A picture of a butterfly. And what do butterflies do? They metamorphose. They emerge from the cocoon as butterflies. And process is called metamorphosis, and we're going to look at how rocks and slime do this as well. Metamorphose means to change. So just like butterflies metamorphose in the animal world, rocks do too. There are, as a quick review, 3 different types of rocks. There's igneous, that's formed from magma or lava, like a volcano or deep within the earth. There's sedimentary rocks that are deposit on the Earth's surface or underneath oceans and form into rocks. And then there's metamorphic. So any of these 3 rocks, including an already metamorphic rock, can change into a metamorphic rock, as long as the rock stays at least partially solid. If it melts completely, it becomes an igneous rock. So then it's not metamorphic anymore. But how does this happen? There are 3 main ways. It's by heat, by pressure, and by fluids, usually water. So let's start with pressure. You can apply pressure to things kind of in 2 basic ways. You can apply pressure all sides more or less equally, or you can apply pressure on certain sides more so than other sides. You can also pull things apart, or you can compress them or squeeze them together. So such rocks are called non-foliated when you sort of just do things equally on all sides. And generally speaking, their minerals stay in the same random pattern that they were in when they crystallized. So you can pull this apart kind of if you just let something change due to gravity, kind of the natural forces. That will result in an extension, or you're going to pull it apart or extend it kind of on all sides equally. You can also compress something on all sides equally. That's going to be something like packing together a snowball, if you've ever done that. And you're just going to keep packing it on all sides until it becomes a nice round hard snowball. And pressure can also be kind of directed on 2 sides or opposite directions, more so than other sides. So if you've ever had like a piece of taffy and you've just pulled it and pulled it and pulled it until it finally broke apart and it kept getting thinner, that's going to be one example of extension. That's kind of directed on 2 sides because you're using your 2 hands to pull it apart. And you can also push something together on 2 sides and not on the other sides. And that will, that's called directed pressure because you're directing it on some certain side. You're not just putting it on all sides equally. Such rocks are called foliated, and their minerals tend to migrate in ways that kind of reduce this stress. They're trying to kind of get out of the way for this. So we're going to take a look at this and do this with slime and experiment with some of the different ways that you can put pressure on slime. So in this case, for example, brittle is when you break it. So if you think about, and the slime will do this, if you pull it apart as far as you can, eventually it will break apart. And that is a breaking, and it's called a fault. So it's faulting rocks. You can also bend it, and those are those bottom 2 pictures with the yellow highlight in them is some examples of rocks folding. And we call that folding versus faulting, bending versus breaking. This is more of what's called a ductile deformation or changing the rocks. And so this would be like pulling and bending, folding things, and you'll do that with your slime as well. So you can also slide things past each other. So if you think about, like, if you've ever taken a library book out and then you wanted to put it back in the crowded bookshelf and you had to kind of push that book into the rest of the books on the bookshelf. So that's an example of doing that. So let's take a minute now and do some of these experiments with our slime. Hi. Now, once you get your slime, you might want to describe it, observe, take observations, even take a picture if you want to of your slime. You can take a picture because you're going to be doing a lot of different experiments, and it's fun sometimes to look at a before and after photo of your slime. If you don't have access to a camera, you can always draw it. You can make a sketch of it, and you can use colored pencils to fill it in and give it the color that it wants to, because we are going to be possibly changing the color of this also. For right now, though, let's just examine, do a few experiments to examine and describe how the slime changes as a response to pressure. This is kind of like how rocks are going to change in response to pressure and make metamorphic rocks. One thing you can try is you can try some directed pressure on two sides versus all four sides at the same pushing it together, like making a snowball. You can try that. It tends to ooze out, but you make a snowball there. You kind of squeeze it into a ball. Another thing you can do is try to squeeze it out. And for this, you might want to set up a measuring tape handy, and then just very gradually, as gradually as you can, move it out and see how far you can stretch it before it breaks. Remember, this is just like metamorphic rocks, where sometimes they bend in response to stress and sometimes they break. Here we are bending it. And I have made it to, I'm going to call it quits, I've made it to 15 inches. Beat that if you can. So that is extension, or pulling apart. Here's breaking, or faulting. That also happens to rocks. And then here is the squeezing together of it into a ball. Okay, done. Here's another example that you can do. Now this is a rock. Well, this is your slime, but we're going to think about this as a rock deforming under pressure. And in this case, the pressure is going to be gravity. Gravity is going to want to make this slime flatten out and kind of spread out on this paper. And in real life, rocks do deform due to gravity. So the first thing you want to do here is roll this kind of into a ball and put it on a piece of paper. It doesn't have to be graph paper, but I've used graph paper. Trace around it really fast. Then use your trusty stopwatch. Hit start. Okay. And then just observe. You can also take a picture before, and you can take a picture after, whenever it flattens out to your liking. Generally speaking, this could become really boring if you sat here and waited for it to become like one atom thick. So I don't think we'll wait that long. I think we'll just wait a little bit until this starts to become flatten out. And until you can see, if you zoom in, you can kind of see where the outline used to be. So you can tell that we're already making progress. We're flattening it out. And that's the one nice thing about this slime, is kind of translucent, so you can see through the trace that you did before. So if you have a lot of time, you can just wait and see exactly what happens, like after an hour. We've now let it go 1 minute on the stopwatch, so I'm going to trace around again. and see where it is now. And then I'm going to show you kind of what happened. So we're going to stop it at about 1 minute 22 seconds. And we're going to peel it off. And we're going to see that it flattened out about 2 squares on all sides. When you just estimate, it's a true estimate or a guess. It flattened out about 2 squares on all sides of the slime. So you can do some experiments like that, let it run out maybe for an hour or something like that, and see how flat it gets. Great, done. Okay, and now that we have done some of the slime experiments, we're going to look at actual rocks and get an idea of what those do as well. So here's some actual rocks in San Francisco, and you can see the folding that has taken place, kind of like what you've done with your slime. And what you can get is a series of different rocks when you direct the pressure or make it heavier on 2 sides than on all 4 sides. You can move from the rock on the top there, which is just regular sedimentary shale, all the way through slate, phyllite, schist, and then finally gneiss. Let's take a look at each one of these. Slate is the first one that's formed from pretty gentle directed pressure. So that's squeezing shale down into something that's a harder rock. Here's a whole bunch of slate. This whole mountainside is slate, and this picture was taken in Norway. And you can kind of see where that slate is. It's got a real smooth surface on one side. Looks like a giant slide. Slate is used for building materials, and in this case it was used for gravestones. These are hundreds of years old, and this is in the Boston area. And the flat surface made for a really easy way to cut those and break them up into different gravestones and then inscribe them. Now a little bit more directed pressure will form schist, and this is when the minerals are actually starting to realign themselves and you can start to see it visually. So schist has a lot of sparkliness to it, and that's the mica minerals, and then you can see that great big garnet in the side of that rock. That's going to show up as one of your beads. Now a lot of pressure will produce something where the minerals will rearrange themselves to try to get out of the way of that pressure into a rock that actually takes on a striped appearance, and this is pronounced gneiss. It's not spelled that way, but it's pronounced gneiss. And the way to remember it is by a really corny geology joke. Don't take it for granite. It's really nice. Now, there's other features in metamorphic rocks, and these are patterns that you can find in different metamorphic rocks. We'll look at 3 of those today, and then you'll look for them in your slime. The first one is metaconglomerate. That's where the pebbles are actually going to be stretched. The second one is augengneiss, and the third one is boudins. Let's take a look at metaconglomerate. Here's where the pebbles actually get stretched due to the pressure. So you think of pebbles as being round because they're rolling around in a stream. Well, in this case, they've actually gotten stretched and they look more like ovals. The next one is Augen. That's German for eyes, and so they kind of take on an eye shape where they're pointed at either end and kind of round and thick in the middle. And the third one is boudinage, which is a French word for sausages. So these kind of have that bulby shape in the center, and then they thin down in between, kind of like a string of sausages all linked together. Now here's one more. What do you think? Do you think this looks more like a boudin or more like an augen? Okay, now that we're done with that, we're going to take a look and see some of the slime and try to make these different patterns, the stretched pebbles and the boudins and augens, with your slime. Now we're going to relate the slime a little bit back to metamorphic rocks. If you did this experiment where you made the ball of slime and let it flatten out, you can tell that it was equal on more or less all sides. as it flattened out. It got bigger by about 2, more or less, 2 squares on all sides of it equally. That means gravity acted on this equally on all parts of the slime blob that it started out as. And that's true for non-directed pressure. There's no specific place, it's more or less equal on all sides, just like this ball is equally acted on by gravity to push it down and push it flat. If you direct the pressure, you can make some of those features that we looked at in the PowerPoint, such as algae. You can make it look like an eyeball if you want, kind of like, and that's a pressure. And see how I'm like pushing it on certain areas at once? And you can make boudins, which are those sausage things with the they're like little blobs with thin parts in the middle of them. So there's a boudin, sort of. Here's one. Wow, and there's breaking. This is a fault in the rock. When rocks break, they're faulting. When they bend, they're folding. So bending versus breaking. So you can try to make algans and boudins if you want, and stretch this out to almost make something that looks like a gneissic rock. Now another thing you can do to make some more observations about how rocks respond to pressure is to add some new things in. You have a bunch of bags of different materials. Take out first your foam balls. These are the ones that are bigger. They're not the candy sugar. They're a little bit bigger than that, and they like literally weigh nothing. So they're really staticky, so they fly all over the place. I'm going to put them in this container, and only a few. We gave you way more than you need. And then I'm going to try to incorporate them into the slime. And if you try to do this and mush the slime around, you'll notice that you can deform the slime, but you really can't deform these foam balls that are in it. They are like non-deformable. It is kind of fun though to mush the slime around and around until those balls are sort of suspended into the slime. Then you can try your observations again. Try to stretch it. See what happens. Observe what happens to the foam balls. Do they become like that stretched pebble metaconglomerate, or do they stay pretty much round? Try to make algae. Try to make boudins. So, anything that is cool and interesting, go ahead and take a picture of or sketch it and color it. Don't forget to color it because there's a lot of interesting colors in here. Now when you're done for the evening, because this is all the experiments that I have to suggest to you, so you can think of more, and if you do, please write down what you did, take observations, take pictures, and maybe you can show them in the final flip grid that we do in our celebration of learning. But when you're done for the evening, because we'll pick this up on day 2 again, you can store your slime in here. And you just simply put the lid back on. And if you want to be extra cautious, you can put it back in the plastic bag that it came in. And then we're all set for tomorrow. One final word is this little cup. If you don't really want to, like these foam balls are easy enough to pick out if you don't want them in there anymore. But as we get further along and we get into incorporating some of the sugar balls and the marshmallows, you might want to divide up your slime so that not all of it is subject to the change that will occur. So that's what this little cup is for. In the meantime, we will see you again on day 2 when we do more slime experiments.